the fragility of life, so let's all ponder that.
I did it, yeah, so, okay, good. So it's great to be back at ITAMP, okay? I left ITAMP about 25 years ago, and it's always great to be back. I will spend a month here in the spring during my sabbatical, okay? So I hope for more good things to come, and I'm going to start with this plot, okay? So this builds upon Eric talk, okay? So Eric talked about 50 years of development in EDM precisions. Okay, so this plot is so it covers the millennium. Okay, so this is how the accuracy of timekeeping has improved over time. Okay, and you could see that this axis here is a linear axis, and this is a logarithmic axis. Okay, so and the Moore's law on this log linear plot is supposed to be linear. Okay, what happens here is that you see this exponential improvement over time. Okay, and it's amazing, right? So like it means that each new technology that comes in, it has a steeper slope. Okay, so and to me, it is a surprise. I cannot explain it. Maybe it is some sort of psychological or sociological phenomenon, but the fact remains that the new technology always brings a steeper slope of improvement. Okay, so in fact, this plot is outdated. Okay, so now the optical lattice clocks and ion clocks are somewhere here. Okay, so and the student that has drawn this plot has long graduated. Okay, so I don't have the original data anymore. Okay, so just trust me. Okay, on this one. So and we have heard a couple of talks about new emerging technologies where the probably the points are going to be somewhere here. Okay, so and the speakers have given a great introduction to these new technologies, and I just would like to remind a couple of things that that I was involved in. Okay, so and so this is a paper that has shown that a nuclear clock indeed can have this much better improvement in atomic timekeeping. Okay, so in the 80s, Eugene Kale from Moscow has pointed out that a nuclear transition in thorium might be used as for clock applications. Okay, so and then Neckerpike and Tam wrote a paper saying that, hey, there are two possibilities in this field, ion clocks and these solid state clocks, okay? So, but they cannot estimate how far they can push this technology. So in this paper, we got together with Alex Kuzmich group, and we have shown that indeed there are certain schemes where you could reach 10 to the minus 19. So this is 19th decimal place. Okay, so and so the point was that so the great feature of this paper was a realization that to get to this level of accuracy, you need to decouple electronic and nuclear degrees of freedom. Okay, it's not sufficient to just have a nucleus that is small. Okay, so you also so if there is an external perturbation, it's going to affect electronic cloud, and this electronic cloud is going to affect your nuclear degrees of freedom. So in this paper, what we have done, we have decoupled those degrees of freedom by choosing stretched states. So the stretch states are product states of the electronic cloud and the nucleus, okay? Then they are decoupled and only then you could get to this level, okay? That was the point of this paper. And by the way, connecting to what Juni was telling, and some of today's speakers were also referring to, so there is, so we have, so this line here, the gravitational line. So it comes from a clock comparison, and these two clocks sit in the gravitational potential of Earth, and they are all by a single aluminium. Okay, so that is where 10 to the minus 19 comes from. Okay, so now in the same year, so it was clear in 2012 that probably it's going to take a while to get to that to find that nuclear transition. And yes, okay, it took 12 years, right? So we heard the talks from the first day about this, right? And driven by that, we published a paper with the Sydney group where the paper, so it was about highly charged ions. Okay, so we had to talk about that. So and in this paper actually we have done a careful analysis. So it was the first full-fledged proposal of how to use highly charged ions, and we have estimated systematic uncertainties, and they were also at the level of 10 to the minus 19. Okay, and that was so. I looked yesterday at his paper. So the motivation that I wrote was that the nuclear clock, however, relies on yet unobserved optical transition in the radioactive thorium-229. Here we show that the nuclear clock performances can be replicated with atomic systems, fully overcoming this challenge. Okay, so great, right? So and then this leads me to this minus 30. Typically, when I give talks about atomic clocks, people ask me, what is heritician doing in this highly technical field, right? Okay, so and my answer is it. Okay, so well, our experimentalists, they do these magical things, you know, they perform almost miracles. Okay, so they can walk water, but it is up to us to show where the stepping stones are and actually where this path might lead. Okay, so look, I hope this makes all these theoreticians feel.
Yeah, your microphone seems to have gone off, but I don't know why. Maybe battery.
Well, we need an experimentalist, right?
More battery.
Okay, I'll go.
Good. So now let's talk about clocks and exotic physics. So I've shown you this estimate of various systematic effects, and the claim is that all these conventional physics perturbations are well calculated. Okay, so then we could use atomic clocks as sensitive devices to search for some exotic physics, and to do that, however, you need certain signature. Okay, so you cannot just go in the lab, see some deviation in the frequency, and say, hey, this is a good physics, right? You have to have a certain signature. Okay, and usually when we talk about exotic physics and atomic clocks, we talk about variation of fundamental constants, and this is a brief introduction to what fundamental constants are. But the basic idea is that in the physics beyond the standard model, the constants become dynamical variables. Like Masha had this example of theta QCD that became a field. Okay, so then if these constants they become dynamical variables that can vary in space and time. Okay, so and this is a classic experiment on the slow drift of alpha. Okay, alpha is defined structure constant. So this is a clock comparison at NIST. Okay, so they have done the clock comparison. So it is a comparison of the frequencies. So they have done.
Yeah, I think it would.
It's
That's
today,
a
a year from now.
Double A's.
Yeah.
Triple A's.
Okay.
All right, give me 1 second. Is there any underneath?
Right. So and well, I didn't see any drift. Right, there are much better experiments nowadays, and but I like this experiment because I visited it during this run, and that is a truly classic paper. Okay. So now, okay, so that was that. Right now, over the past decade or so, we look at the variation of fundamental constants in a different way. Okay. So instead of just being slow drifts, okay, we can talk about transients. Okay, so and these transients could be induced by, say, some dark matter models, so clumpy dark matter models. They could be so they could be due to the microstructure of dark matter. Then oscillations. You need it,
It took a couple actually.
Oh, it took a couple, I see. Okay, so another models of dark matter which are not clumpy, they lead to oscillations of dark matter. But if you even look at how how the dark matter velocity distribution looks like, it leads to stochastic fields, and this stochastic fields leads to the stochastic backgrounds in variation of fundamental constants. Okay, so and all of this are, of course, you're motivated by ultraviolet dark matter. Although I should tell you that actually oscillations of fundamental constants, for example, they are present in Kaluza line models that are much older than this ultraviolet dark matter business. Okay, so all right, so how do we search for dark matter? Okay, so clocks monitor atomic transition frequencies. Transition frequencies depend on fundamental constants. So then we could search for variation of fundamental constants that are consistent with dark matter models. Okay, so and that's why I was talking about signatures, right? So if it is a transient, I could search for a transient. If it is oscillation, I could search for a peak in the frequency space, right? And this was our, I believe, first proposal that proposed to use atomic clocks to search for clumps of dark matter. Okay, and the basic idea is that I have a nominal value of the fine structure constant outside of this block. Okay, and inside of it, I have alpha that is different from. And going back to Eric's talk, so yes, it is the poltergeist type of new physics. All right, you agree? Yeah. Okay. So and then we started the project that look, I'm not an experimentalist, okay? So, but yeah, in this particular case, I had a collaborator, Jeff Blewett, who was an expert on global positioning system, and that community has about 20 years of data, okay? So, and we started searching for these transients in GPS, okay? So, and here you see that a wall moves through and it paints all the satellites red, right? And that is the signal. Well, I mean, we look, of course, at the frequency spikes that are propagating through the network, okay? So, good, and it has some limits, so we will probably publish some new limits soon, okay? But basically, these are some energy scales, and these are effect size, or you could also talk about the mass of the field, and indeed these are this ultralight dark matter candidates. Okay. All right. So now let me go into the main topic of this talk. Okay. So I told you that we only have 20 years of data. So what if this transients occur on a time scale that is much longer? So like suppose the rate of encounters is 1,000 years. Okay, so you have an encounter every 1,000 years, then of course we are not going like the probability of us seeing this transient in the data is super small. Okay, so okay, but we are just limited by 20 years of data. Okay, and then you had the pandemic, right? And during pandemic, you start thinking about life and and other things, right? So okay, how about we use humans as dark matter detectors? Okay, so that is the basic idea, and this leads me to this anthropic constraints on transient variation of alpha. Okay, so what is the anthropic principle? Life can emerge and be sustained only in a narrow range of values of fundamental constants. Okay, so for us, it seems like it's not entirely, I would say, a comfortable thought for a physicist, but for a biologist, so if you go on, so if you want to catch a fish, right, you go to a river, right? Okay, so and moreover, so actually it is from about a couple of weeks ago. I was on a fly fishing trip to Mongolia, so we were helping this conservation efforts for timing. Okay, so and this is a biologist, and she's not surprised by the anthropic principle at all. Okay, so okay, so. And right, so she also tells me that that timing is highly sensitive to environmental factors. That's why they have this program of conservation. Okay, so and yes, I did catch it. Okay, on the fly. It's even more challenging. Okay, so so a typical example when was that people invoke when they talk about anthropic principle is this generation of carbon-12 in stars. Okay, so we are a carbon-based life, right? So it turns out that this carbon is generated in this triple alpha process. Okay, so you have two alpha particles coming together, so that they form this beryllium 8, but beryllium 8 lives for super short time, 10 to the minus 16 seconds. Okay, so for carbon to form this third alpha particle, so it has to recombine with this beryllium nucleus very fast, and this is only possible due to foil resonance. Okay, so it is some resonance state in carbon 12 that enables this entire process of generation. So if this resonance were slightly moved, okay, so you would not be forming carbon 12. Okay, so and this is the basic idea. Yeah, so yes, of course, without this resonance, the universe would lack the carbon needed for life, and then it would not be here to talk about. Right? So okay, good. Now, so if you start looking at the literature, okay, all of these constraints, they come based on ideas that this alpha variation, for example, is going to affect all the stars. Okay, so if I have affected all the stars, then I don't generate I don't produce carbon 12, right? But for a transient, I'm going to affect only a small subspace Okay, so then these anthropic constraints, they do not apply because the carbon 12 could be produced outside of this block. Okay, right? So it is an important point, the point that I argued about with the editors of the physical review letters, and I still haven't convinced them. Okay, so but it is a subtle point. Okay, so there are no anthropic constraints on the transient the variation of fundamental constants. Okay, so all right, so okay, so how do we set these constraints? We know that the life has persisted on Earth for the past 4 million years. Okay, so now if I have a block of some sort that sweeps through Earth and substantially affects the conditions for life, okay, then I would be setting a constraint on how large. So so then I would be setting a constraint on a transient. Okay, so it turns out that this variation, so it's about a factor of 10. So if you, for example, reduce the speed of light by a factor of 10, okay, you will be in trouble, and I'm going to talk about it. Okay. Okay, so there is a certain theoretical change here. Okay, so series in the audience should appreciate it. So if you look at the literature, all these previous computations, say from Victor Flambaum group, they are about tiny variations. Okay, so here the variation of fundamental constants is going to be huge, and this huge variation of alpha, they are going to lead to dramatic qualitative changes in atomic and molecular structure. Okay, so I'm going to talk about it. And every time I am on campus of University of Colorado Boulder, and if I go to Gila, okay, so I always remember Gamov, right? So it is a Russian name, okay? So to me it means a lot, okay? So and Gamov has written a series of popular books, okay? And in one of these books he was talking about Mr. Tompkins dreaming about a world where speed of light was much smaller than its nominal value. In fact, he was talking about speed of light that was about 25 miles an hour, right? And then it's a beautiful world. You don't need speed limits in this world, right? You don't need police, right? So, but then, right? So pandemic, right? You start thinking about this. Is this even possible? Would life be possible in this world, right? Okay, good. So let's talk about this. Okay, so the thing that one needs to understand is that relativistic approach is a must. Okay, so the fine structure constant is here. So the nominal value, I don't need to spell it out to this audience, right? So and the ratio of the speed of the electron to the speed of light is about alpha. Okay, so if I change alpha to 1, I'm going to get exaggerated relativistic effect. So it is going to be this Mr. Tompkins law. Okay. So and to deal with this properly, you need to solve the Dirac equation. Okay. And I'm not going to write it down. Okay. So, but I'm going to show you what happens. Okay. So first of all, for a point like nucleus for hydrogen, solutions of the Dirac equation do exist. Okay, so the analytical solutions do exist, and this is the point like nucleus. So if you start increasing alpha, okay, so if you get, so this is 1 minus alpha square root, right? So if I get alpha that is greater than that, the argument of square root becomes negative, right? And it means I'm going to get energies that are going to have an imaginary part. What does it mean, right? We all know that if energies require negative part, it means decay. Okay. So what actually happens there? Okay. So and we have solved this problem numerically, because actually what we needed to do is to do this properly. You really need the finite size proton. Okay. So the spectrum of the Dirac equation, so it includes positive energies, it includes the negative energies. So these negative energies are field, these electrons, so this so-called hierarchy, right? And then, so we are going to increase alpha, okay? And when I reach alpha, so this is the nominal value of alpha, okay? And then this 1s, the ground state energy dives in, and at some point it dives into the hierarchy. At that point, you start producing electron-positron pairs. Boom. Okay. Hydrogen atom goes boom, and it happens at about alpha about 1. Okay. So, all right, good. So then you could go and look at the Mendeleev periodic table. Okay. So and do the computations. Okay. And what happens here? So this is the nuclear charge. So the first thing to understand is that the V over C for charge ions becomes alpha Z, right? So if and critical alpha is when you get this ratio of about 1. Okay, so then you get so the critical value of alpha when the 1s orbital dives into the hierarchy. So it determines actually when a given atom becomes unstable. Okay, and what happens, for example, here is that when alpha is increased by an order of magnitude, the entire periodic table shrinks to elements from hydrogen to sulfur. Okay, so for example, if I wanted to get rid of the nuclear weapons, right? Okay. For example, right? I'm going to generate a field like this, right? I'm going to send it, okay? It's going to pick out the uranium or plutonium, okay? And I'm done, right? No more works, right? Okay, so good. So but then so if you plug in numbers, actually it doesn't work. Trust me. Okay. All right. Okay, good. Now let's kind of go back to this. Okay, so where was this plot? No. Yeah. So what happens the hydrogen is that the fine structure intervals become huge. Okay, they become so huge that actually some of the levels start to change order. Okay, so it means that if I go to the usual Aufbau principle, so if you open any undergraduate textbook on quantum mechanics, there is Aufbau principle of how atomic orbitals are filled, right? And what happens here is that at the critical value of alpha, or the critical value of the speed of light, so you get 2p3 orbital going up, okay? And then neon, for example, neon has 10 electrons, and all of these orbitals here are filled. So that's why it is chemically well inert, right? But now if you have this new Aufbau principle, you get instead of a closed shell system, you get an open shell system, and so in fact the C that is 10 times smaller, neon becomes carbon light. Okay, so then in that universe you could have neon-based light instead of carbon-based light. Okay, and so by the way, I'm avoiding showing you all of these computations. Okay, so it is just a result of actually of ab initio yes.
Just a quick question. Does the nucleus even stay bound if alpha is so large and the protons push each other apart?
I'll get to that. Yeah, I'll get to that. Great question. Yeah. Okay. So let's talk about water. Okay. So water. Okay. So this magical substance that we do need for life, okay? So, and a lot of properties of water, okay, like the hydrogen networks, the ice floating on water, it is related to this angle, okay? So, water is a balanced molecule, okay? So, and when we increase alpha, okay? So it turns out that at some point, the rearrangement of atomic orbitals that our Bohr principle has shown you, it leads to the molecules straightening out, okay? So, and the linear molecule, linear triatomic molecule doesn't have a dipole moment. You have the dipole moment, you don't, okay? So then water no longer serves as a solvent, okay? So you're in trouble in terms of life, okay? So you cannot pull these other molecules apart because you don't have the dipole moment anymore, okay? Good. Now let's talk about proton, okay? So, and okay, so I was proud of this paper, and I immediately have sent it out to my particle physics friends, right? And both of them, both Alex Kostenko and Maxim Popospelov said, how about you look at the proton, you know, if proton is stable? Because look, what happens is that, so in our world, proton is stable, but neutron lives about 10 minutes or so. And it decays to proton plus the positron and antineutrino. Okay, so and but proton is stable because its mass is lower than the mass of the neutron. Okay, so now if you start changing off, okay, so this proton to neutron mass difference is very subtle, in fact. So it comes because of the cancellation between electromagnetic energy and quark mass splitting. Quark mass splitting, it is the difference between the masses of the up and down quarks. Okay, so but the electromagnetic energy is that because you have the proton is charged, right? So if you take again some undergraduate electricity and magnetism class, you actually can compute that electromagnetic energy just by assuming that the charge is spread uniformly. Okay, and so, but in fact, there were some latest QCD computations about this mass difference, and they also look at the change in alpha. Okay, so and it turns out that if you drive alpha to about 10 alpha naught, okay, so you reduce the speed of light by a factor of 10, it spoils this delicate balance, and you open this decay channel, so the mass of proton will become larger than the mass of neutron. Okay, so and then you get radioactivity and atomic electron capture by protons. Okay, you're in trouble, all right? So it seems like there is something about this factor of 10 that is quite critical for supporting life on Earth, right? So and then the rest of this is just some series of computations that is not that different from what we do in GPS DM collaboration. So if I just assume a quadratic coupling to this scalar field, so this quadratic coupling, it changes alpha in fact, and I could place the limits on lambda. Okay, so lambda is the energy scale, and then you get limits that are several orders of magnitude better than the limits coming from astrophysics. Okay, so how much time? 5. Okay, great. So all right. So I have talked about transients, right? I skipped oscillations and stochastics, and now I'm going to just spend a little bit of time talking about oscillating transients. Okay, so it is another regime, right? And this type so this regime could occur in multi-message astronomy. Okay, So, and for example, we might see them in black hole objects, okay? So, and I'm going to skip this. So, suppose if I have some dramatic, super energetic event, right? Then there are some exotic fields that emitted. I have a clock here, and so the question is, can I see this in my clock data? Yeah. Okay. So now, and you all have heard about mathematical astronomy. So it is so Newton star merger. So and this event that has been seen in gravitational wave modality, it has been seen in the magnetic spectrum, right? So, but can we see this in this exotic beyond the standard model field modality? Okay, so all right, so that's actually the papers that we wrote, and Shimon is here in the well, that's another. Sorry, yeah, so. Oh, yeah, okay, good. Also, yeah. Okay, so yeah, so yes, exotic low mass fields, you have heard Masha talking about them, motivating them, right? I'm not going to repeat this again. So suppose I have a merger of some sorts, right? So it emits a pulse of these exotic fields. How is this pulse going to look like at sensor? What is the signature? Okay, so the fields are massive. So what happens in fact? So if you look at the propagation of this this initial Gaussian packet, is that the faster components of course are going to arrive earlier. Okay, so and the faster components also have higher oscillation frequency, so you are going to see an anti-chirp signal. In live it is chirp, but here you are going to see anti-chirp signal. Okay, so and yeah, so I'm going to skip this. So and what you would like to look at? Okay, so you get gravitational wave propagates at the speed of light. Okay. These are massive fields, so their group velocity is of course smaller than the speed of light. But they must be relativistic, so that way I get a LIGO trigger, okay? And then I get this arrival of these massive fields, but I like the delay to be reasonable, okay? So, and what we've done, we again looked at our GPS data. So it is actually, so it is for the merger for this neutron star merger. So, and there are 2 days here. So it is the standard deviation of the clock frequencies averaged over the entire network. Okay. So, and you see this blue line. So it is the blue trace here. So it is on the day before the event. So this is the LIGO trigger on the 17th. Okay, and you kind of see some sort of an excess of the signal. Okay, so we of course are excited, right, and all of that. But it turns out that the GPS satellites, they have ion and the solar wind sensors right on board. So you could read those off. Okay, so it turns out there was this enhanced emission of enhanced flux of ions and electrons from the sun, and I think this actually is due to this. Okay, so instead of this exotic physics. Okay, and on this note, I'm going to stop. Thank you.
Couple questions.
So, Andrei, great talk. I remember you gave one, and I think I asked a similar question at Wisconsin or something when you came and you spoke, but like the variations you're looking at are for this with this anthropic principle are really big, I think. but in principle, can you find like some crystal that would only form in the ground that's more sensitive to alpha? And then if we find it and it's a billion years old, like in a rock that's a billion years old, we know that alpha wasn't different a billion years ago. Like, are there kind of subtler chemistry that we can still handle that's still tractable to see if alpha changed by a part in 1,000, or is it really only possible to look for these really big?
It's a good question. I don't know. This good answer. So just we just worried about these big things, right? So yeah, it's a good question.
Okay, so this is absolutely wonderful that you're entertaining this idea. The question here being asked all the time, right? There's a lot that when we go through the domain wall, something dramatic can happen. We also know that, you know, there's dark matter in our galaxy and some rapidly go over the lifetime there. Well, we went around the center of the galaxy, 20, right? So does your limit come from that? If, I mean, they would probably bring you to some sort of a limit on the density of your, how dense your structure could be, and give you a limit how often that something like this has happened, and if it didn't happen, derive how much change.
Well, in our estimate, so when I saw those limits, I took the dark matter energy density 0.3 GeV per cubic centimeter, so it is the fixed number, right? And I guess are you thinking about so
No, but we
that
actually need it.
about
Yeah, yeah, but-
density could change.
Yeah, not the audio.
Yeah, if you're available, right, so that all the energy would be.
Well, it's kind of so it is related to the limit on the couple.
This guy needs-
All of this